The Hong Kong Polytechnic University, PolyU, leverages its world-class academic and research excellence to develop innovative solutions for a more sustainable tomorrow. In July 2022, the PolyU Academy for Interdisciplinary Research PAIR was established as the university's central research platform, dedicated to providing world-leading, interdisciplinary solutions to significant societal challenges. PAIR is composed of multiple constituent research institutes and research centers. Each research unit focuses on a particular research area and is joined by researchers from various PolyU faculties, schools, and departments. These research areas broadly fall under three main themes, including advanced technologies and manufacturing, good health and well-being, and smart and sustainable cities. PAIR researchers develop new materials, systems, technologies, and techniques that support industrial modernization, upgrading, and transformation. Look into the factors and mechanisms influencing human health and wellness and develop evidence-based solutions. And generate smart technology-based solutions for making urban operations and services more efficient, connected, and eco-friendly. We particularly value impactful collaborative activities in research and scholarship. PAIR researchers pursue research collaboration at different levels. In addition to interdisciplinary collaborations within and between research units, PAIR and its units establish partnerships with industries, governmental bodies, universities, and other external stakeholders. With internal and external collaborations, we have successfully translated PAIR-led innovations into commercializable solutions and practical applications, and established joint laboratories and research entities with external organizations, driving scientific breakthroughs, innovation and technology development, and socioeconomic prosperity. PAIR's research excellence and research impact have been widely recognized at local, regional, and international levels. Our research outcomes have been published in leading journals, including Nature and Science. Innovations led by PAIR researchers have won prizes at various competitions and events, including the International Exhibition of Inventions Geneva. Many PAIR researchers have been named among the world's top 2% most cited scientists in their own areas of specialty. Individual researchers have been selected to the National Academies of Science or Engineering and as fellows of professional associations, and have been bestowed with local, national, and international awards and honors. Harnessing the strengths of PolyU's research and world-class scholars, PAIR will continue our unwavering efforts in research and scholarship, knowledge transfer, and collaboration to develop impactful solutions that benefit Hong Kong, the nation, and the world.
Good afternoon, colleagues, ladies and gentlemen. Welcome to this PAIR Distinguished Lecture Series. My name is Chen Xiaodong. I am the Director of the PolyU Academy for Interdisciplinary Research, or PAIR. So today, it's my great pleasure to introduce our distinguished speaker, that's Professor CHEN Xiaodong, who is a distinguished university professor at Nanyang Technology University, or NTU, Singapore. So Professor Chen is known for his development of soft materials for application in flexible devices, energy storage, and healthcare. His research is highly interdisciplinary, transcending the boundaries of fields from materials science and engineering, flexible electronics technology, service and interface science, to carbon negative technologies. So this is a very important subject for today's society. So at the NTU, Professor Chen is a professor of material science and engineering with a joint courtesy appointment in electrical and electronic engineering, chemistry, and medicine. So you can see this really go beyond the science and engineering into the medicine. He has also leads several research platforms, including the Innovative Center for Flexible Devices. His research group developed a method for controlling the architecture of materials at the nanoscale, offering powerful solutions to some of the humanity's most pressing challenges, from climate change to healthcare advancement. Among those innovations include smart sensors that come in various sizes and thickness. Sometimes it can be thinner than just the width of a human hair. It's so thin. Also, like the water-responsive supercontractile polymer, a kind of biomaterials. It can contract by more than 50% of the original length within seconds after wetting. So Professor Chen's work has a profound impact. He holds over 50 patents, 9 of which have been licensed for commercialization. He is currently the editor-in-chief of the journal ACS Nano, and an elected fellows of the Royal Society of UK, that's the Royal Academy of Science, the German National Academy of Sciences, Leopoldia, and the Singapore National Academy of Science, and the Academy of Engineering Singapore. And I'm very proud of him because he's also my country fellowman. We speak the same dialect. We can only speak by only a few million people. Both of us are from Fujian Putian. So without further ado, ladies and gentlemen, please join me in welcoming Professor Chen.
Okay, thanks for Professor Chen for kind introduction, and also thanks for invitation. Have a chance to be here to give a talk, especially under the PAD distinguished lecture. I really enjoy the time here, and I'm really looking forward the next bit 1.5 hours to really having more interaction with the students here and also staff faculty. I mean, the way for this field is really interdisciplinary about this kind of bioelectronics interface. But this is really need a lot of this efforts for different people in different backgrounds. And then today's, I'll be honest, today my talk, I try to be a bit unusual talk. The way I try to be really kind of brief, introduce what I'm doing. And then also a lot of topics, I didn't really go much detail. Because usually if I give a talk, I go very detailed. I usually one talk about 1 hour, I only talk about 3 papers. But today I really cover all we are doing about, not part of our doing in the last about 15 years in the conformal bioelectronic interface parts. So let's start first, why we want to do this project. So conformal bioelectronics is really kind of emerging field, but there must be a reason because this kind of emerging or paradigm shift in the human-machine interface. And human-machine interface, in fact, is not new words. I know a lot of people know, oh, this is kind of very hot topic, but in fact, not. You can see in most areas use this kind of Windows. And this is kind of machine, it's more like we have to adapt to a machine. You can see when we get a deep kind of a command, you need to type in the words. And later development, you use a lot of this kind of figure base. But now, today's a lot of this kind of human machine is based on this kind of AR, VR, this kind of technology. It's a kind of human-centered, different kind of language, right? Kind of by visualize or by this kind of large language model. It's language-based, typing-based, and so on. So they can nature language-based. So this is coming for nowadays, this kind of human-machine interface. But looking forward, because technology, we always know we are looking for about another 20, 30 years, what's going to happen? And so also we know, because this kind of technology development, make our nowadays life is a lot of different compared to before. So the same as the machine fit. Tomorrow, how this kind of human machine looks like? For the early generation, we have to adapt to human machine. We have to adapt to a machine. But more coming will be more about this kind of immersion, this conflict, this kind of more smart, this kind of behavior. And also involve multiple this kind of intelligence. It's also two-way communication. So this is kind of future this kind of human machine interface. And then of course, people still, oh, how this kind of human machine look like? I can give you 4 examples. You know how future may look like. So robotic surgery, exoskeletons, wearables, some are coming now. For example, for this kind of robotic surgery, usually doctor, you must do this kind of surgery standing there. But in fact, nothing nowadays you can see for this kind of Da Vinci, this kind of robotic surgery. Use this kind of visualize for doctor just sitting there to do this kind of surgery, this kind of precise this kind of surgery. But future will be more this kind of two-way communication, not only from visualize, could be many this kind of 5 sense involved there. So the future robotics is coming as future robot surgery. Exoskeleton is not about help, right? So because now you can see exoskeleton really make this kind of individual strong. Future could be two-way communication, involve this kind of human, a lot of this kind of human machine interface, especially for this kind of brain machine interface. So this kind of neuron-based technology will be involved in this kind of exoskeleton to make this skeleton perform even much better. For wearables, not about data, you want to get data. In the future, wearables really do this kind of contact list, a lot of this kind of institute, and then give you immediate this kind of response, how this kind of behavior looks like. And then involve many kind of technology to do this kind of treatment. Okay, this kind of interment. So this is kind of paradigm shift in this kind of human machine interface. And then of course now people ask, well, Prof CHEN, these 3 topics can be different. So what are we going to talk about, right? In fact, these 3 parts, they share one common part about sensor. How do you get data, high quality data? So there's kind of fundamental challenge there. But for sensor, it's not so easy. You know, here in fact, sensor, a lot of issue about sensor dysfunction under this kind of deformation. But deformation could be many parts. Let's give you an example. So this is kind of the top line for the blue curve is ideal data. So the requirement from professor to students, right? Okay, I want to get this kind of data, sensor information. Like this kind, the middle one is about this kind of ECG, we people know already, right? But of course, in this case, even our students work very hard in the lab, 26 hours per day for 7 days a week, right? And then you find a problem is always get this kind of information, the bottom one. The bottom one is the kind of signal drifting. This is the motion artifacts because it's kind of dynamic. So, and also this kind of signal distortion. This is very, very common. This is not because students do not work hard enough. It's because the sensor itself is about physical property. For example, the motion artifacts. For motion artifacts, you can see, maybe if you do, what's motion artifact? Many people this kind of Apple Watch or this kind of smartwatch. When you want to measure this kind of ECG by the watch, what do you do it? You need to have this kind of 30 seconds, no movement, right? It must stop there for 30 seconds to get ECG. Why have this kind of static ECG measurement? Because this kind of motion artifacts there. So what I mean is, give you one example. When you put electrodes on skin, and then you will find for electrode on skin, so have this kind of epidermis with dermis, you can have this kind of the middle one, it's kind of equivalent circuit. And the right side is the formula. The impedance, strong related is kind of capacitance. But capacitance or strong related is the distance between electrodes and epidermis. So in this case, the small change of distance of this electrodes with epidermis will lead in a big change of this kind of capacitance. This will lead a big change of this kind of impedance. So this is a consequence. That's why small change, small this kind of unstable one, to leading the big change in this kind of impedance. So this kind of impedance instability, leading this kind of motion artifacts. So let's give you examples. So that's why the fundamental challenge for bioelectronic interface is how to get high quality data, reliable data. But there are 2 kind of challenges there. First challenge is a mechanical mismatch. For human, we are composing mechanical materials. Soft like a kilopascal like a tofu, rigid like a bone is a gigapascal. So it means 10 to 6 times or 5 times this kind of magnetic difference there into this kind of mechanical properties. But for conventional silicon-based, this kind of property in terms of silicons, only one part of properties in mechanism, 110 gigapascal. So that's a kind of mechanical mismatch there. The second mismatch is language. So we know already for biology system, human, is a chemistry language. It's an immediate language, a chemistry language, it's molecular interaction, whatever, any kind of interaction. But our digital world is 0-1 languages. Now you need to translate from one language to another language. Very difficult to understand, right? Just now, Professor Chen mentioned already, we speak same dialects. Then Zhijian cannot understand for sure. Then you need to build some channel, allow this to to understand each other. So same as this kind of electronic with this kind of molecule or biology words. So that's kind of analog to digital transition, leading a big challenges to get reliable data. So that's why my group put a lot of efforts to how to use materials to be the key driver to such kind of technology transformation. Give you examples. Silicon, 110 gigapascal. No way can really be a kind of adaptive interface built with these biological systems. So that's why we do this kind of materials path. For example, polymer base could be 100 kilopascal up to 10 megapascal, even rigid. So this allows bridge this kind of rigid with soft. So this kind of fundamental part, we played a lot of efforts there. So in this case, let's start, because for bioelectronic interface, of course, involve many parts, right? You can see conform. Let's go back for my title. Conformal is about mechanical. Bioelectronic is bioelectronics. Interface is about this kind of chemistry material interface. So we are very kind of interdisciplinary. Then we start with the first one, electronic parts. You want to build this kind of bioelectronic interface, you must have this kind of electrodes. How to build bioconformable electrodes there. And flexible electrodes and all stretchable electrodes is not new research. In the last almost like 20 years, a lot of research evolved in this field. Of course, there are few pioneers like Professor John Rogers from Northwestern, Professor Zheng Bao from Stanford, and Takao Somiya from University of Tokyo. So these are a few people play very important role to drive the field. For example, Zheng do a lot of this kind of semiconductor-based, this kind of organic-based or polymer-based, this intrinsic materials, stretchable materials. So this is really kind of a big, quite a lot of developments there as well. What John is doing to develop this kind of suspended structure, in fact, he used a lot of mechanical design to build this kind of suspended structure. A lot of this kind of silicon-based materials can be stretchable, be bendable, make it thinner as possible. So this is made by mechanical design. But of course, other approach by material-based, pre-strength approach, or crack-based approach, and so on. So these are a few approach people use this to build this kind of flexible and stretchable electrodes. Every approach has the pros and cons. No perfect solutions there. And then, in fact, we started more than 10 years ago. We also developed this kind of stretchable electrodes. My thought is very simple. I want to use the most reliable materials. Most reliable, one of reliable is gold. I like gold. It's not about price. It's really stable. A lot of electrodes, a lot of sensors always use gold as this kind of materials there. So that's why we're starting to ask our questions. How can you make this kind of gold be stretchable, right? Usually gold cannot be stretched. Less even, it's stretched as much as 5% will break already. And then what to do is we develop this kind of nano approach to build this kind of ribbon, gold nano belt ribbon. So this by lithography you can build it. But we transfer onto pre-stretch this kind of PDMS and a release. In this case, on the metrology parts, you look at this kind of gold can be stretchable. But in fact, it's not because intrinsically stretchable. It's more this kind of mechanical design structure. So that's why our stretch goal can be stretched up to 130%. It means for 1 centimeter, I can stretch to 2.3 centimeter. So looks fine? Yes, can be published paper, but only for publication. Why? This kind of material is extremely unstable. Why? You can see for gold, when you stick on this top of this kind of PDMS by non-covalent bonding, bond-wise interaction, easy peel off. So although this paper, we do a lot of animal trial to prove it works, but only works in a paper. Scientifically, it works out, but it's not stable enough. So that's why we ask ourselves, how possible to make this reliable gold nanostructure on PDMS? And then of course, people always ask, okay, maybe it's not so difficult, right? You can go on the PDMS, also find directly. But it doesn't work. You can see I put this kind of scotch tape on top. Just easy peel off. It means not stable. So let's go back ask ourselves a question. What be the fundamental science challenges there? You put this kind of gold with PDMS. This is more about the adhesion, work adhesion between gold and PDMS, interaction. How to enhance interaction between two materials? Let's go to this kind of fundamental physical chemistry questions. And in this case, you can see for gold with tape, the adhesion is pretty strong. It can go for 100 joule per meter square. But for gold elastomer, it's really weak, 0.07. There's almost a 4 magnitude difference there. So that's why gold is easy to peel off from elastomer or from polymers. And then according to this kind of energy criterion, we found you want to increase adhesion between this kind of gold with polymers. There are few possibilities. Either you do the surface modification, or increase contact area, or do this kind of new chemical bondings. So in this case, we choose the second one. It's possible just by increase the contact area between the polymer and the gold. Let's allow this kind of gold can be stretchable big enough. So from this perspective, we develop an approach called mechanical interlocking. So what I mean by mechanical interlocking? In fact, we artificially build this kind of nanostructure of gold, and then make this kind of gold in polymer, polymer in gold. So in fact, the fundamental reason is because they increase adhesion, contact area between gold and the polymer. So in this case, according to Jaeger adhesion theory, they will increase adhesion between the polymer and gold. In the meantime, because this case build this kind of contact between this kind of friction between the gold and polymer. So this kind of two kind of reason to really enhance the gold and the polymer interactions. In fact, our experiment proved it works. So you can increase almost 10%, 10 times of this kind of adhesion between the gold and the polymers. This is our this kind of nanostructure, gold in polymer, polymer in gold, this kind of nanorod structure. The strength can go for almost like a 2.5 megapascal, compared with others are much, much lower. So that's why it's about 10 times enhanced. But this one is this template approach. We use this kind of AO as template to grow nanorods and then pulling over PDMS. Although it was, but very, very time consuming. So that's a kind of challenge us another possibility, further develop it to even simple approach, have this kind of go in PDMS or metal particle in PDMS. This is kind of science development. Then we go back ask one question. Why you spend so much effort there, right? Just as I mentioned already, because gold with polymer work adhesion is very weak, small, 0.07. The reason because when deposit is kind of gold on solid substrate, the gold usually has kind of 2D diffusion model, growth models there. That's why you can see if you people in this room, you do this kind of microfabrication, you know, when gold deposit on this kind of silicon substrate, usually you must have a coating of nickel or chromium, have adhesion layer. So that's the kind of reason because increased adhesion. But now for gold doesn't work out, right? But we still want it. It's possible have gold transfer into this kind of substrate. So this case, solid substrate work well. And then ideally we come from this kind of polymer. So the polymer materials, they have this kind of so-called interpenetration polymer network. One polymer, another polymer, they interpenetrate. Then I ask ourselves, it's possible gold can also penetrate in this kind of polymer. Gold penetration or diffusion in a polymer. So this can become our scientific questions there. And then in this case, solid substrate doesn't work out. That's why I ask ourselves, if solid doesn't work, can we use a fluidic substrate? Right? And then gold can penetrate in this kind of fluidic substrate. So that's why we built our hypothesis. Is gold diffused in this kind of solid substrate, but in between our mechanical interlocking parts. So this is three together building our research development lab. So the gold in polymer substrates. But we know already, solid substrate doesn't work out. It's a fluidic substrate, but fluidic is very difficult to process it. And these parts exactly use our polymer chemistry. PDMS is type of this kind of polymers. It's really fabricated by this kind of polymerization between this kind of monomer with this kind of cross linker with a certain ratio. So this is a kind of a base, AB. CD is the curing agent. This is all commercially available. You can purchase from this kind of from Dow, commercially available. The people in this room, you know the polymer chemistry, much this very simple. Traditional polymers being used in this kind of thermal, a lot of this kind of microfabrication. And because for this kind of PDMS, they found this kind of network structures there. And also we know, for this case, dependent time, right? From beginning 0 go to 40 minutes, the beginning is kind of liquid state. This is the solid state. In between, have this kind of transition state. So that's why I ask ourselves, I don't need to deposit on this kind of solid state, but I can deposit just between half a QS status, a lot of oligomer of a PDMS, like oligomer. They have certain kind of fluidic states that can be processed. So that's what exactly in between. So this kind of, we call semi or half cure, this kind of half cure of this kind of materials there. So in this case, we call this approach called thermal radiation assisted metal encapsulation. So why I call this one? Because we know when we this kind of you're heating to deposit the metal, this temperature can go to 1,000 degrees. But close to the interface part, the temperature is about, because thermal radiation, the temperature is about 80 degrees. So 80 degrees is really helpful further polarize of oligomer of PDMS. So it means the process go penetrate in this kind of oligomers. In the meantime, the oligomer further polarize. Let's go in PDMS. This is how it can build up. Of course, seeing is believing. Let me tell you how this looks like. This is now. Now this is stretchable gold. This is a conformal, stretchable, bendable gold now, right? Just not very difficult to process. Now it's really easy to process in these kind of polymers parts, stretchable, bendable. And also you can see the back layer is a black color. Do you know why it's black color? It's not black carbon, it's black gold. Because when the gold nanoparticle aggregate together, because this kind of, I didn't control size there, randomly, so that's why it aggregate becomes this kind of black color there. So this is further evidence our approach hypothesis there. It works. In the meantime, it's very stable. For this gold, we put this kind of glass, it's very easy to peel off, but this kind of Scotch tape. On this kind of fully pure PDMS, it's also easy to peel off. But on our approach, it's very stable. You will see, it will not peel off. So this kind of further evidence how stable for this kind of materials compared with our usual approach build up. And then now people ask, why this approach is such kind of stable and stretchable? There are two reasons. If you go to this kind of cross-section part, the cross-section is really has gold film, in between gold PDMS composite, and the bottom one is a PDMS substrate. So that's now, you know, it's kind of mechanical interlocking. In the meantime, you look at this kind of morphology by FM, you can see this the structure here, a lot of kind of wrinkle-like structure. This is like our skin. You know, our skin, what can be stretchable? Because a lot of these kind of wrinkle structures there. The similar case, now our gold is also this kind of wrinkle structure there. So that's why gold can be stretched in our case there. So this is kind of parts why it works out. But of course, meantime, you can just kind of mask. I can build this kind of gold particle array. You can now you can really go this kind of array in everywhere, depending on what your size you want. By lithography, you can easy to make up. So not only two-dimensional film, could be microelectrode array and so on. Then can use for many applications as well. I will not touch too much today. But we also, sometimes my student also do some experiment, come out 3 cases, right? Of course, I may always show you good parts, conductive, stretchable, bendable, very stable. But if you look more experiment, then we can have a 3 kind of case will come out. First case, this is kind of stretchable. So this is kind of stretchable parts, right? I mean, this could go in PDMS. It's very going to diffuse inside. This look at the cross sections there. But for this case, you know, once gold is really diffused in this component, it will not conductive. So that's why conductivity very low. It can resistance almost 10 to 11 ohm per square. And then for gold polymer adhesion, of course, easy peel off. This first one. The second case is very good conductivity, like a 30 ohm per square. So this is the middle one, case 2. And also very good adhesion between gold and polymer, more than 600 Newton per meter. And you look at this kind of cross section, you see the cross section on top, it continuous gold film. On the bottom, gold in PDMS. Have this kind of diffusion inside. This is case 2. And for case 3, gold is really easy to conduct. So this gold, this bottom is a PDMS, but easy peel off. So this is a typical 3 case we observe in this lab, in our experiment. Of course, ideal case would be case 2. Case 2 would be most ideal one. Stretchable, conductive, good strength, good adhesion strength between this kind of gold and polymer. But now we ask ourselves a question, why? Why it happened for case 2? Rather, case 1 and case 3, we also can observe as well. So that's what we spend time to understand. But now I can tell you, yes, now we really understand how gold in PDMS now in polymer systems there. We do our experiment. We can control ratio between this kind of polymerase agent with this kind of monomer. From 10:1, go to 40:1. 10 is more rigid, and 30:1 or 40:1 is more this kind of soft. Now you can see the more soft, gold can penetrate more furthermore, diffuse in this kind of PDMS. If for this kind of rigid, gold is still on top, very difficult to penetrate inside. This is by XPS measurements. You really do this kind of line by line scanning to see where's this kind of gold positioned. So this is how we can observe this kind of gold PDMS interface this kind of film formations there. And then for this case, we work our modeling people. We found the line is really modeling line by this kind of fixed law. The dot is our experiment data. From here, we can really measure this kind of diffusion constant or this kind of gold nanoparticle in a polymer. For a few cases, from 10:1 up to 40:1, we get all this kind of diffusion constant. Now you can see the more rigid, the gold is very difficult to penetrate. The more soft, gold is easy to penetrate. You can see this is almost like a more than 20 difference of this kind of diffusion constant. So this is the first time we can measure it. And then you can see compare this kind of diffusion in the pure solid state with the polymer liquid state. We are in between, right? This is the idea also same. This is based on our hypothesis. We are calling this kind of semi-pure polymers. Suppose this kind of between polymer with a solid state. So this kind of further evidence of early hypothesis exactly how gold nanoparticle diffuse in this kind of polymer matrix. And with help of this kind of particle jumping simulation, now we can visualize how the gold penetrate in this kind of polymer matrix. This is use this kind of 20 gold nanopore deposition in this kind of 20:1, this kind of rigid thickness there. Then we can really, of course, you can do and more, 10:1, 20:1, 30:1, 40:1. So this is kind of experiment how I understand this kind of diffusion of a gold in polymers there. And then this is somehow how I understand how this kind of continuous conductive, this kind of gold film formation, stretchable conformable parts. Because this is give you kind of one type of experiment is gold in PDMS. But in fact, in my groups, we have various polymers parts. Now, we summarize together is we can really achieve this kind of stretchable gold, more like 400% stretchability. From 1 centimeter can stretch to 5 centimeters. It's also electricated and anti-conductive, and extremely conformable, and also durable adhesion, can up to 190 Newton per meter. So that's kind of how further dimensions already. And for such kind of electrode can be used for various application. For example, on this kind of skin-based device, we build out a lot. And also this kind of implantable device. In fact, here dotted line is our electrodes, the stretchable electrode. We can use this one to build this kind of neural interface, human machine interface parts. The last right side is one of our first early prototyping, how such electrodes can use this kind of prosthetic control. Later I will show you the detail how it works out. Okay, so this is basically about materials parts, how can we achieve this kind of conformal electrodes in device. And then in very early stage, we also do this experiment application, right? I mean, people always interested how this one can be done. For example, this is our electrodes. We put on this kind of muscle to get this kind of EMG. Use EMG to control prosthetics. Of course, this is really nice control. This is 1:1. You can see this is kind of EMG data. You can get EMG from this electrode, get EMG data, use this one to control this kind of prosthetics. Very nice one, but only for in the lab. Why? Very difficult to really, I mean, repeatedly. I'm not going to repeat it. It still can be repeatable. But the question is, if a small change of place, you need to do a lot of fine tuning. And also you can see the connection there, right? This is very difficult. I mean, in the lab it works, but cannot move out to do in other lab as well. So that's just kind of challenges the stability, reliability, connection. This is because this kind of connection issues there. So that's why give ourselves questions, how is possible have these integration parts together? Then in fact, this is exactly the current challenge for flexible electronics, soft interconnections. So many people, if in the audience, you're in the field of flexible stretchable electrodes. We know already there are many different electrodes, diodes, sensors, and also flexible transistors. A lot of new research is going on now. But for industrial application, people care about how you can build this kind of multifunctional integration device, and then go for various applications. Then we're missing one gap, is interconnect. How you can interconnect with different components into this multifunctional stretchable electrodes. In fact, I can use one analogy to tell you. For human, we know organ important. But we also know the joint also extremely important. If you have an issue with a joint, you will limit your functionality, mobility, and so on. So in the same case, soft connect also play important in the flexible electronics to build different components together into a multifunctional stretchable systems. So that's kind of solve integral problems there. And then why have this kind of issue there? Here's this mechanical simulation tell you why always a lot of kind of happen in this kind of interface, interconnect parts. You can see the left side is our rigid paste. The right side is our stretchable modules. When you increase the total strength, you can see in the joint parts, always have this kind of concentrated strength there. Such concentrated strength will lead in this kind of a big change of stability of the whole device there. So that's a kind of challenge for us. How can you develop this kind of reliable, soft interconnects? And then, if you just now remember, for the case one, for this case one is gold impedance. Gold is simply diffused in this kind of impedance. But we know already it's not electrical conductive. And also PDMS do not have this kind of self-adhesive properties if you do this kind of connection there. But what to do is, we change the PDMS is photosensitive materials into the thermoplastic elastomer, SCBS. So this SCBS is also well-known start results already. SCBS connect with CSBS, they will diffuse together. So this comes from self-healing properties there. So that's why we come up with one hypothesis. Can you replace SCBS with PDMS? Then when going SCBS, now I can contact together, they'll self-heal and become this kind of like interconnect. So this is our hypothesis come out. Because this one, of course, do experiment. Now let's experiment how to do it. We'll deposit gold particle in SCBS. This gold particle can diffuse in SPS, no problem. That's our long-time experience already. Now what I do is, because it's diffusive, I do this kind of paste contact. In this case, I have two components. The exposed SPS use this kind of for self-healing. But for gold, use for this kind of contact, electrical conductive. So in this case, I can build this kind of biphasic nano-dispersed interface, in short, called bind interface. So we call how we call bind interface. So in this case, we can build a three case as well. Usually, if a gold nanoparticle density is very low, in diffuse PDMS, it's SPS, whatever is adhesive, still non-conductive, as so by here. You can see the density is very low, it's non-continuously. So that's why this is close one is contact FM measurements. Okay, this is kind of non-conductive. But when certain high kind of gold particle density, I can build this kind of conductive, this kind of soft connection. If the density is too high, if it go fully cover SCBS, they are conductive but cannot be adhesive. So that's why I have three parts. In the middle part, we define as the combined connection. The left side is non-conductive, right side is non-adhesive. Now, of course, we can do the systemic experiment. By this kind of rate is gold rate, this gold particle diffusion in the substrate, and also thickness. We have three phase diagram. The bottom one non-conductive, the middle one connection, the up top one non-adhesive. So this kind of protocol we can build up. Because this kind of interface there, now I can reach almost the this kind of what we call this kind of stretchable connectors there. So we get all this kind of commercial available, this kind of connectors from ACF tape, copper tape, carbon tape, and so on. You can see whatever this kind of electrical stretchability or mechanical stretchability, usually less than 60%. They stretch to 60% break already. Like this one, this uses this ACF. You can see the stretch, electrical stretchability less than 50%, mechanical one less than 70%. 76%. It's break already. But use our case, we can reach electrical stretchability up to 180%. Mechanical stretchability go to 600%. So this is kind of our data. So that's why I can see our data is always far more than beyond our experiment parts. So this ensure this kind of stretchability issues there. Now, once this one soft software can be connected, then many things can be done already. For example, I can do this kind of fully customize this kind of stretchable circuits there. Very simple. This materials, band connection part, stretchable electrodes part use our approach. Even interface part also use our approach. But for a lot of this kind of circuit can pre-design. You can use this kind of other resource. Okay, we see people, this one easy to do in Shenzhen area. Just ask them to place order, we place order through Taobao. Then in the next 2 weeks, they will send to us already. They can build out fully stretchable, flexible circuits already. You can see this is our technology. The remaining one, you can use other kind of resource to build up. Then build this kind of fully customized, flexible hybrid circuits. This is how we can build up. But of course, this is something you must have from our own group. And because this one now can mean do many things, right? Give you examples. So in this case, we can do this plug and play. These parts I can commercialize. We can get from commercial resource. And then once to come in, just plug and play. Then can connect already, use our stretchable electrodes. For the neural link, what they do is you must do this kind of full package and then embed in your brain. But not for us. We just use this electrodes there. So that's why we prove various this application, but I don't touch the detail how we build up and how to do it from ECOG, from bladder stimulation, from this kind of muscle activation and so on. We can, the neuron size can for few hundred, the organ size can few hundred nanometer up to micron, even larger. We can build this kind of electron interface there. This is how we can do it. Yeah. But even can do it, still facing some challenge about signal qualities. Okay, can you see this is more we can do left side. Although what we do what we want, but I can see the commercial electrodes still a lot of challenges. Cannot really get reliable data enough because a lot of this kind of crosstalk, and also the signal knowledge is not high enough. Although our electrodes works well, but it's not full integration. So that's why we push ourselves further challenging. How can you really further enhance the signals there? So this is why EMG is really also very challenging. But of course, we need to ask ourselves, why the noise is such high? In fact, it's a fundamental physical chemistry questions. Let's give you an example. In fact, just now, we mentioned a bit already. When you put this electron on skin, there's this kind of double layer here. They have two double layers here. This is one double, another two double layer. So this two double layer will determine your impedance levels there. Okay, but unfortunately, a lot of electrode, usually a lot of this kind of air gap inside. A lot of air gap. This air gap leading to big change of this kind of impedance layer, very high impedance layer. So that's why we summarize all our current data. You can see we have different kind of electrodes on skin. All the impedance usually more than 100 kilo ohm. If for our human skin, impedance skin, the intrinsic skin impedance is about less than 10 kilo ohm. So it means there are 10 to 100 magnitude, 10 to 100 magnitude difference there. Okay, so there's a kind of different times difference there. So that's a kind of leading challenge about because weak interaction between epidermis with conducting layer. Now, how can we enhance interaction of these two phases? It's become one of the challenges there. We also know already for skin, usually skin a bit hydrophobic, right? This will be an error or not. But unfortunately, a lot of cases we do this kind of electrode, use this hydrogen electrodes. Hydrogen is electrically, I mean, kind of hydrophilic. So that's why we hypothesize ourselves. It's possible to add in certain kind of hydrophobic components in this hydrogel to increase this kind of hydrophilic interaction between this kind of skin with polymers. So this is kind of our approach. We call molecule anchoring. Have this kind of non-polar components in this kind of membrane. So that's kind of our idea come out. Because this, now we do this MD simulation to confirm our hypothesis. We start with alginate. Alginate is hydrophilic hydrogel. DOPA, relative hydrophilic already, but we reduce it to be hydrophobic. Acrylic, even more hydrophobic. QEP, even more. Now you can see, start this one more polymer will penetrate in this kind of membrane there. So this gives our ideas it will be this one, will be increase this kind of adhesive, meantime also reduce impedance. In fact, the answer yes. Sorry. Now, because this penetrate inside, in fact, there's another more data proven here. So this is why you can see, give our direct evidence, the alginate will not penetrate in this. This is a pig skin, very clear parts. But this one, PVCl, is kind of our polymers, but it can penetrate already. The interface is about 3 micrometer. This from a few hundred nanometer up to 303 micrometer. It's very kind of broad distribution. Because this, now we change this formula. Just now, this is the 200 nanometer interface there. Now I can go for micrometer. This means the small change in this interdistance will not make big change of this kind of capacitance. That's why keep this impedance pretty small change. So in this case, overall, we can see this is our data to show adhesive increase, the meantime impedance reduce. So this is kind of our data. Because this now we can really use for this kind of application, for this kind of low impedance microelectrode arrays for prosthetic control. Because this is also involved discipline research from electrode fabrication, AI, also do this kind of data sorting, analyzing feedback, allow to build this kind of control system, and then leading this kind of control. So this is kind of fully control this kind of prosthetics there. The 16 channel come from this here. You can see this is electrodes. This one, use one signal difference. This all this action leading to control this prosthetic to grab this candle up, and then to also position to where there's another hole here. Again, all this one because here. So this is kind of muscle EMG control this prosthetics there. So this is kind of our early generation one, use this one, and to build this kind of human machine interface parts. But of course, now even we not only about EMG, we also can do EEG now. This is kind of EEG, use similar electrodes. This one also can control this. This one can be car and so on, could be many kind of application. But tell you how such kind of device integration systems allow building machine interface to really control many things you never saw before. This one just control direction. But of course, many even more fancy function can be developed by this one. Okay. But of course, here, maybe because time limitation, I will skip a bit quickly. But basically, this is about technology for NTU parts. We can build this kind of conformability, stretchability, Young's module close to human skin. In the meantime, we also reach this kind of low impedance plus this kind of high detection sensitivity. Can be with some commercial variable samples. We are in quite pretty kind of advantage position. But now we are translate this technology to start a company to really further to develop our own parts, more even advanced technology for commercialization application parts. And then finally, I'll give you maybe about 5 minutes to tell you another part is about this kind of This just now is over 2-dimensional. But in fact, in our organs, the 3-dimensional, dynamic, very dynamic. It's not like this kind of electronic circuit, it's kind of standard circuit interconnection parts. Because biological systems are very dynamic organs with different individual variations there. And people try to ask a question, is it possible to build this kind of soft material? Can be really adapt, conformable to many change parts. So that's a kind of question to ask as well. And in a lot of cases in this kind of cathode electrodes, they try to, but the question cathode electrodes leading China about this kind of either too much high force or too hard to stretch, and they will damage this kind of immune response there. And then also, in fact, the scientists also try to figure out this kind of ship wrapping electrodes to build this one, do this kind of conformal interface. But it still need a pre-designed parts. Then ask ourselves, can we develop certain materials, can be certain kind of water response, conformable, and also any kind of shape you can be applied? The answer is yes. In fact, we inspired from spider silk. So spider silk exactly is kind of have one property is a simple construction. When it connect with water, you can see immediate simple construction. Then from here, we ask ourselves, can we build this kind of artificial materials? Have similar properties as spider silk, this kind of simple construction? The answer is yes. And of course, we start with beginnings because for spider silk, have one property is kind of beta shear structure inside. Yeah, of course, when design structure, we also map a similar beta design structure, beta shear structure. Meantime, it's also one other structure of this kind of beta strict crystal this kind of domains there. From this perspective, then we build these materials. These are response materials. Now you can see water contact immediate response there. Because this one, there are few properties there. Stable, rapid response, you can see in 1 second can shrink almost 30%. You can shrink almost 65%. Soft, like 100 kilopascal, stretchable 600%. In the meantime, it's also compatible with a lot of this kind of electronic fabrication. We can simply put electrodes on this kind of substrate. This kind of field properties there. Here, we name this material called water-responsive superconductor polymer films. You can wrap, right? It's exactly wrapping this kind of properties there. So this is how we build up, in short. And then the materials composition, I cut a very detailed how to build up. I just give you the result here. The material itself, very simple. PO with the PEG, this is well used in biocompatible materials. In the meantime, use this kind of casting film to build this kind of isotropic thin film. Isotropic thin film that will not be water responsive. And then we use this kind of for a cold drawing approach. Do this kind of repeated cold drawing. This one, a lot of the material can be stretched from 0% up to 100%. Because it's stretchability, now this film can be water responsive. You can see we put this one in the water, immediate contact with immediate construction, simple construction, just touch with water. And then the middle one, you can see the red one more is kind of stretch soft. This is almost like 400% is hydrogel. It's hydrogel-like structure. So this is exactly the kind of water-induced simple construction there. And if you're interested in what detail, can really look with our papers there. They will give you very detailed how this material will build up. It's a lot of this kind of, in fact, we spent almost 4 years to do this research there. And because this one, now we can use for this, a lot of this kind of application. For example, this one can use this kind for this kind of electrodes. Wrapping conformal electrode. Doesn't matter about any kind of size of this kind of tissue or organ, like a neuron here. Build everything already, just put a drop of water on top. This electrode can be conformal contact already. And then this one allow you to do this kind of stimulation. You can do this recording. This one can activate movements of toes there. But of course, even we do this kind of minimal invasive implantation as well. So this, for example, this one, you can transfer this kind of film into a small hole. This is kind of the rise and the mouth of this kind of heart there. Okay, I mean, this is kind of even more. This is kind of in situ. So that's why you can see the heart is beating there. We can transfer this kind of membrane into this heart, wrapping this kind of heart. Then can in situ measure the heart status there. So this kind of experiment you can build up. Of course, even fluorescently, we can put this one to build this kind of control this kind of neuron muscle functions there. So the middle one is neuron. This one is our conformal electrodes. Then I can do this precise control. This precise is very important, like this one. This one control result, and then I can use this kind of music to control this kind of frequency. Use this frequency can control the movement of the toes. You can see this is the low, and also this is the more. It's very fast response. Okay, so this is kind of, we have a lot of experiment going on now. But in short, sense the word, pursue future, create energy property. This is exactly how this kind of conformal flexible electronics parts we are doing now. But of course, this is just beginning. In fact, we are pushing a lot of effort. Just now I saw you about electrically, mechanically. But in fact, we now put a lot of effort for chemistry. Chemistry is really beginning now. Why? This involves this kind of sense technology developments. In fact, we are exactly in the sensor 4.0 now. It's connect many components together, especially now highlight a lot of this kind of chemical monitoring. Once they have this kind of variable chemical monitoring, plus the current kind of status, then a lot of things can happen as well. But one thing I want to really like this one is called nullius inversa. So this is kind of from Latin. But what that means? It means take nobody's word for it. Okay. Science is always like you have to really experiment to demonstration, to validate what people have said. Seeing is believing. This is the motto of the Law Society. I really like this one. And this is something to help to drive the research going on. Yeah. So finally, thanks for our students and also our funding agency, because this is students funding agency efforts to really support our research going on. Of course, we still recruit student postdoc. Also, we're also looking for funding support. If anyone, you don't know where to spend money, you can donate to us for research. All research costs a lot of money there. Okay, finally, thanks for my collaborators, a lot of collaborators helps us a lot. And also thanks for our students. Welcome to visit Singapore. Thank you for attention. Happy to take any question you have. Thank you.
Okay, thank you so much, Xiaodong, for the very exciting talk. I think we've got a Q&A session, and I'm Zijian Zheng from ABCT. My great honor to chair this Q&A session for Professor Xiaodong Chen's talk. So I think the way that this session carry out, basically you guys can turn on the microphone. There's a button over there if you want to ask question, or if you're a little bit shy, you can raise your hands and let me know. Okay, so I think we've got roughly about half an hour, roughly, right? So this is a great opportunity for those, especially for the junior research staff and students who really maybe read Professor Xiaodong Chen's paper before and would like to ask questions, or if you want to challenge him directly, face to face, right? Okay, I think that now the floor is open. Anyone want to start with the first question? Yes.
Testing. Well, thank you, Prof Chen, for inspiring talk. And I'm just thinking, like, how did your technology improve the EEG signal recording? Because I understand that it works on skin for EMG and ECG, but is it the same thing for the scalp?
Oh, yeah. So it's a bit of difference,
Yeah.
because for this kind of like EMG part, we use this kind of molecular anchoring approach, right? But for EEG parts, especially a lot of people, this kind of hair issue, right?
Yeah.
So this quiz now it can challenge us. In fact, that one is ongoing on publication. So that's why we use this kind of hydrogel. But this gel is really, in the normal state, is solid state. But on top, we have this kind of, we do this kind of electrode, heating it, make this kind of gel-like structure, can penetrate this kind of skin and even for hair, allow to get this kind of high quality parts. So this is kind of one small trick inside. So this kind of responsive materials we can use.
Is this penetrating biosafe?
It's biosafe, yeah, biosafe. But it's not penetrating on skin. It's just penetrating in skin. It's on skin only. Just penetrate on this kind of hair, because a lot of this kind of polymer, people always have hair issue, right?
And will it be metabolized by the body?
No, I don't think so.
Okay.
And so because this materials are also biocompatible as well.
Okay.
So you can see when I choose the materials, I have a few requirements. First one, you can see if people from materials chemistry, you will see my materials never been completely new materials. Always earth abundant. A lot of like PDMS, SBS, PO, PG. And also now I have a more kind of consideration about biocompatibility. Because if you go on skin or implantable, biocompatibility is one of the big challenges as well, right? So that's why I use PO, PG. So this is our requirements as well. Yeah. Even still, if people read our paper, right, I also use a lot of silk as well.
Yeah.
So that's kind of a part we have a ribbon. But of course, we must do this kind of certain kind of modification to really adapt to the properties we need. Yeah.
Thank you.
Thank you. So, anyone else? Gang, you want to talk to your old friend? Yes. You're hiding there.
Yeah, I'm hiding here. I'm still junior. Still a lot of things to learn. Yeah, one simple question is, so how close for this the bioelectronic the interface can go to the real life? Can you give any comments on that?
This question is not simple.
Yeah, everything is not simple. People know sitting on the floor.
There's a kind of commercialization from the lab to the bed, right? There's a lot of gap there. So I think for me, I didn't really push a lot for translation commercialization using our partner work on health, or even our other kind of research, kind of more business people background there. But I think for me, it's really make sure this technology readiness level be higher. If we can grow readiness can higher than 5, 6, 7, then the industrial collaborator stepping quickly there. So that's why I'm more trying to bridge the gap there. So this is our fundamental question. And so that's why when I choose this kind of materials, I make sure it's really easily to scale up. Scalability, you can make it can be scaled up. The second requirements, these materials or this device fabrication is really compatible with the current technology. For example, I like this kind of microelectronics. When you develop flexible electronics, if you ask us a slow the current microfabrication technology approach, that's completely wrong. You need to really think of how we can adapt to our current microelectronics technology, right? How to build this kind of soft, rich interconnect. Once you can build a soft, rich interconnect, then rigid part don't worry too much. Soft use our own property. So this is kind of our approach there. So that's why we try to use like based on our current technology can become more reliable. In the meantime, develop our own strategies there. If we talk about if this one can work out, then it's really on the way to translation. And also, in fact, for bioelectronics, in fact, not just now we can see a lot of this kind of, let's give you an example for this kind of glucose monitoring, continuous monitoring. This is also bioelectronics, right? Glucose, continuous monitoring or daily glucose monitoring. It's all, but the only problem is now how far away from the outer body, on body, in body. Then you have more requirements there. There's a kind of step-by-step challenges there. But it's only because it's a big trend there.
Your groups is already one of the most successful groups move forward in this field. So Zijian just sitting beside. So as a friend, also as a competitor. So how you work together each other to move forward in this field?
Well, we are not competitor, we are more complementary, everyone knows Zijian is rich, right? So that's why I always try to close.
Super rich, yeah.
Yeah. So that's why, I really saw my technology. Hope, Zijian can buy my technology. Then I'm fine enough already, right? Because I think different people, for example, like for Singapore is unique and also advantage to disadvantage, right? Singapore is too, we have very good this kind of research. But we need to really work with the supply chain. But with of course, Big Bay Area is kind of our Great Bay Area is our quite close connections, right? So that's why I think we need to enhance the interaction between Singapore, Hong Kong, or the Great Bay Area. Yeah. So that's why I always approach it Zijian. Even I really one day Zijian can just hire my whole group.
Yeah, thank you. Fantastic.
Just
impressive.
Complimentary to on Xiaodong's. I think for the bioelectronic or soft electronic in general, it's a big field, and of course, many people jump in. Think about I started in PolyU in 2009. Probably only 3 groups in Hong Kong working on this field, and probably about 10 groups in the bigger China area working in the field. But nowadays, it's difficult to imagine that nobody work in this field in a known university, right? So this is a field big enough and interdisciplinary enough to allow many more people to come in. And I think that's a great thing, even though we work in a similar direction, but there are still so many tasks everybody can get their input to tackle the probably similar problems, but in a different way, right? So I think in that sense, we can learn from each other, and we always learn from each other. So I think this is a good field that we work together, we compete with each other, but in a very good way that help each other to move forward. Yeah.
Thank you.
That's a tough question, by the way. Okay. Colleagues and students and postdocs, and any question? I have a few questions in online, but these are written in Chinese. So let me read the Chinese one and probably see if I can translate in English. So the first question, 贴合型生物电子接口的核心柔性可降解材料体系中，哪些关键性能参数，如杨氏模量、降解周期、接电常数 （bracket） 对接口与动态生物组织的长期贴合性及电学传输效率起决定性作用。So I think they are asking like what key parameters of this biodegradable material in your implantable or skin electronics.
Yeah, I mean, I will not call biodegradable, there are a few kind of class people look at, right? So biodegradable means how long time will sustain this electron device in your body, right? So that's kind of, I think, in fact, now it's an emerging field called transient electronics. So transient means one of this kind of polymer can be dissolved automatically about maybe 2 weeks after implantation. But the challenge is not polymer, challenge about metal. I know people use this kind of magazine as these electrodes to do this kind of transient electronic electrode, but still pretty challenging in a way for this kind of reliability. Because if you go for science, just 1 or 2, it works, right? But for translation, application, you make sure almost 99% works. That's the kind of challenges there. Yeah, so that's the kind of, I would say, it's still in early emergent status. And then for it really go for this kind of pure, this kind of, I think I believe the most foundation about not biodissolvable is about biocompatible. Biocompatible first and then biodissolvable later. Yeah. So these are my comments there. Yeah. But of course, a lot of property, I really like these questions. You have different kind of property requirements. But so far, no one in the world built this kind of database yet. Because you need a lot of database to build up, and then you can use AI to work together to find a better materials. Maybe today's about this biocompatible materials, still not better materials yet. Though in this case, you need a whole world or many group work together to build different properties from Young's module, stretchability, or other kind of chemistry, building even modern units. But this one, do not have yet. If this one can be shareable, and then I believe there are many things going on in this field with the help of AI.
Yeah, totally agree. I think there's still a lot more things that can be discovered.
Yeah.
Both some materials, interface and all the others. Well, the second question, also in Chinese, 对于植入式贴合型神经接口, I think this is about talking to something that really new in your work. 其与神经纤维的点对点贴合精度如何影响神经信号解码效率?
Absolutely, there's a huge impact.
Right.
But so far, we don't have this kind of capability yet to really, because this is something, in fact, people start discussing now, how have this kind of high density electron arrays for this kind of human brain interface. So this allowed, you can see for the brain, we have this kind of, I think a lot more like, I think billion of this kind of brain, this kind of neurons inside, right? But so far, I don't have this kind of capability yet. It takes some time. Yeah.
Yeah, especially the tissue are always 3-dimensional.
Yeah.
And it will be extremely difficult, at least for the technology right now. We can't really probe every single neuron in a point-to-point way.
Exactly.
Right. So we can probably do the kind of a patch to many points way. Right. So come up with some sort of resolution, but that's still far away from really point-to-point connection or registration. And again, this is a very good question, but very challenging for the whole field to work on for the next decade, probably.
I would not call, and then it means many students can work together, right? And there's still many opportunities. Challenges always associated with opportunities. Yeah.
Okay, these are the 2 online questions I received so far. How about others? Yes, please.
Hello, Professor. What about the breathability of this material? And do you think it is important to improve breathability of bioelectronics material?
Well, you can see Zhi Jian and Takao. There are a few people on the world that talk about this kind of for breast electronics, right? So this is usually for this kind of skin-based. I think definitely it's very important. No doubt. And then, of course, depending on the application field, it's really skin-based is very important. Yeah. And then this one, Zhi Jian is expert.
I think really recently, we haven't published the paper, by the way, about the work, but we also found that for the implants, breathability is also important.
Okay.
Yeah, so it can be important. So let me go to your question. So breathability is really important because for skin kind of application, it's important to make sure the electronic does not block the breathing of your skin. And in that sense, it will allow comfort kind of wear and a healthy use of your skin electronic for over a long period of time. right? So I think this is one of the major aspects that's important if, let's say, commercialization in the future, that you want to make sure. Anyone else?
Should everyone understand?
I think you today, Professor Chen has talked about quite a lot of this kind of materials. It looks very simple, by the way, but I understand that it's never trivial. Every single step move forward. Since I'm also in the field for about almost 20 years, right?
Yeah, I mean,
Yeah,
definitely.
so
It's a lot of challenge. In fact, all the work we always see it. Let's give example for the super construction. Let's take us 4 years.
Yeah.
From beginning alien to finish it. Yeah.
Yeah, and we have a small story, and I can tell you because my postdoc looks really upset after you publish that paper because we have very similar results and make us very difficult to publish. Your Nature paper. So that's why I said that the good way of competition is that probably we always go similar kind of problems to after everybody, and then we have different way of solving it. And magically, sometimes we come to a similar idea of solving the similar questions.
Could be, yeah.
Yeah,
But
yeah.
another case is also a lot of unexpected incident externally happening, right?
Right.
It's not, in fact, for this simple construction, it's not our early design. People always, in a way, when we talk about story, you always show people very early design. Design is how smart you are, but in fact, it's really accidentally discovery. It just happened for PO, because why we choose PO? PO is biocompatible. And then one day, my student told me, put the PO in the water, it's suddenly simple construction. Then from there, we go back again to study all this reason behind. Otherwise, it's not how smart we are. We just, try to prepare on this kind of, a lot of this kind of unusual phenomena.
Right. Professor Chen.
Yes, well, first, thank you again for a very inspiring talk. I think you have done a great job. I really learned quite a lot, although I am a layman.
Thank you.
Now, when I look at your achievement, right, and especially material is one thing, but from the mechanical point of view, I'm a mechanical engineer, always think about the mechanics, right? So the force, the property, etc. Those also plays a super important roles in the material development. And when we are talking about the interdisciplinary research, so when you develop those type of materials, how important are the mechanical guys can contribute to your research?
Well, absolutely. I mean, it's a lot of this kind of contribution. Even I think it's really part of our research efforts now. You can see our topic, conformable, it means mechanical properties already, right? I think this really appreciate a lot. In fact, I have a very good collaborator, Professor Jian Gao. He's really one of my, and so far we have published more than 20 papers together already. So that's kind of important, I think, play important role. Of course, and you can see especially for recent years, we work with him together. We have a more deeper understanding how this kind of mechanical parts can be early design, can help to really reduce a lot of this kind of trial errors, go to a certain direction already. So that's why you can see, we jointly come up with one concept, mechanical material science. Mechanical material science, how is discover mechanical force to really rational design material properties, in leaving a lot of this kind of performance, emergent performance, so on. So that's kind of for mechanical parts, I think, play extremely important role. Yeah. So but of course, this need a lot of interaction. Huajian, we miss a lot of the time in COVID time. Because during COVID time, Huajian cannot go any place. And then also I cannot go. And then we spend a lot of time together to discuss and have drink tea together in my office, a lot of this kind of discussion. And this come out a lot of new idea how we can test and trial. So that's why you can see a lot of people come together in that 3 years. So that's why I think cross-disciplinary interaction, discussion is really important. Yeah. And especially in the beginning, for me, I do not understand too much about mechanics. Yeah. And then Huajian really is giants in the mechanics. But gradually we learn each other. Yeah. Now he can talk materials, I can talk mechanics a bit.
Yes, you probably know that Huajian was also a distinguished speaker a couple of months ago. Oh. Yeah. Now, you in one of the last few slides, you show the AI stuff there, right? Now, I just wonder now, everyone is talking about AI and trying to use AI as a tool. So can you just share your view on the role of AI in the development of the materials you are working?
Well, that's a big question as well. Unfortunately, I'm not, but I know, for me, AI for me is a kind of tool, right? It's like, people, maybe all students here, same told my students as well. You don't need to be expert in AI, but you know how to use AI. Like you don't need how to build a car, but you know how to drive the car. The same kind of examples, right? So that's the kind of future going on. It's really due to, you can see all this AI, you can see for this kind of ChatGPT, right? From 4.0 straight to 5.0, now it's 5.1, 5.1 now. So you can see the way they write these papers, much better. I can tell you, for me, no way I can write such kind of perfect language in there. But of course, you have to really fine tune, right? You cannot always rely on this kind of machine to write it for you. You have to fine tune based on your personal kind of writing styles there. But in a way, it's really nice tool to have you address many kind of problems. For example, I think 15 years ago when I started as a professor, one of my big challenges is always correction manuscript for my students. I told the students, I'm not an English teacher, right? I have to correct grammar and so on, and also not perfect. But nowadays, when the student bring this paper to me, I don't have this problem anymore because all the grammar is perfect. Now I have to tell them, oh, you need to come back. You cannot write such kind machine type this kind of manuscript, right? So that's a kind of, but I think the tool is really wonderful tool, but you have to do with kind of fun, personalize it as well. You do kind of combination. The same case for materials, for AI for materials. Obviously, a lot of this kind of potential for AI for materials, AI for even for mechanics. I believe, in fact, my student one of them is using this kind of AI with mechanics now, with materials. But the question is the database. The AI database now is for solid state materials much better. But soft materials, polymer, soft materials, a lot of challenges there. So that's why I still need some time as well. But I still believe this really kind of emerging field need many people work together. Yeah. But again, it's also question is how important for this topic, right? If for this kind of protein DNA design become more important, that's why you can see for for biology, for this kind of AlphaFold, right? AlphaFold 2.0, it immediately get a lot of attention, and then many people before use this kind of cryo EM to get crystal structure, but now you need AlphaFold can easily to do it. So this is also pro as a constant. Yeah. But anyway, so everything is two sides. I believe there's a lot of potential for this AI for science.
Thank you very much.
Thank you.
Anyone? Poster or so if there's no further question, I think the time is actually up. So I think we could come back to Professor Chen to give you a closing remark.
All right. To express our appreciation to Professor Chen's contribution, Pear has prepared a special gift. Yeah, this one, as you can see, with your name and your title of top talk today. And also probably. Thank you very much. Yeah, thank you. So I would also like to thank all of you for coming to this distinguished lecture today. And Peer organize distinguished lectures and seminars from time to time. So you are more than welcome to join our next lecture or seminar. Just keep tuned on the announcement we send out today. Also, would like to thank all those audience online. See our advertisement and the announcement as well. So thank you again, and this lecture is adjourned.